In this video, we're going to go about counting the number of triples ABC, where a plus 2b plus 3c is n for a fixed positive integer n. And we're looking for solutions where a and b and c are non-negative integers. And we're going to do this using a bunch of generating series techniques together with some power series expansions. So to get started, I'm going to dive right into the generating series approach. And we're going to use an idea that looks a little slightly different than what we explored in the first video on generating series, but still does sort of the same thing. So the mantra of generating series is whenever you're counting a specific thing, keep track of it in the exponents of a variable and then sum a series in some way. So if we have a particular triple A, B, C, this expression on the right will keep track in an exponent of a variable and will sum over all possible values of A, B, and C. So this will look like the sum C greater than or equal to 0, the sum b greater than or equal to 0, the sum a greater than or equal to 0 of this entire expression. Okay, so if you think about writing this expression, then if we look at the x to the nth coefficient of this entire series, every time we have these non-negative integers a, b, c, for which this expression is precisely the number n, we'll get one term of x to the n in this series. So the x to the nth coefficient of this thing is precisely the number of non-negative integer triples ABC that satisfy this equation right over here. So our goal then is to extract the x to the nth coefficient of this thing. Maybe we'll give this a name, f capital X. So our goal in counting then is to figure out the x to the nth coefficient of this f of x. All right, so to start, one thing that would be good, and this is something that we also did in the previous videos, is to write this in a more compact form. So first you notice that this inner sum depends only on c. So we can actually take out the other terms in the sum, which is x to the a plus 2b, and then have this series for c, which is the sum c greater than or equal to 0, x to the 3c. Now this series here is 1 plus x cubed plus x to the 6th plus x to the 9th, etc., which is the same as 1 over 1 minus x cubed. And again, one way to see this is this looks a lot like the sum of an infinite geometric series. So we can replace this entire thing by 1 over 1 minus x cubed, which we can then take completely out of this sum. So this expression is 1 over 1 minus x cubed times the sum a greater than or equal to 0, the sum b greater than or equal to 0 of x to the a plus 2b. Now we can sort of perform the same process again. We can pull out this factor of x to the a because it's independent of b. So every x to the a is multiplied by one of these. This is a sum of x raised to even powers. So this thing here is 1 over 1 minus x squared in compact form. Okay, so we're left with, we can exchange this entire thing out of the sum that depends on a, and here we have 1 over 1 minus x. Great, so from some manipulations, we were able to determine that a compact form for f of x is this expression right over here. So now we have that f of x is this entire expression right over here. So our goal is to extract the coefficients of this particular series. And that's what we're going to focus on now. So let's say f of x had a power series expansion that looks something like this. d0 plus d1x plus d2x squared plus d3x cubed, etc. So our goal here is to determine what d sub n is. And d sub n, by what we talked about earlier, is going to be precisely the number of non-negative integer triples that satisfy this equation right over here. So in a little while, we're going to actually see a way to find an explicit formula for what d sub n is. But the process we're going to go through gets quite complicated in terms of calculation. If you don't want to get necessarily an explicit formula, but you still want to be able to count d sub n, what you can do is use this together with this series compact form here to find a recurrence relation that the d sub n's satisfy. And the way to do this is to recognize that if this series is this series, then we can multiply by the denominator here to get a large polynomial times this series being identically the series 1. So I'm going to do that calculation right over here, and then we'll see what happens. Doing that, we get that 1, the numerator here, is identically the product of the denominator, which I've expanded right here, times the series that we're interested in. Okay, so let's look at comparing the coefficients of these two sides. So what I'm going to do is pick an integer n that's very large and look at the coefficient of x to the n in this entire series. All right, so we'll have enough terms to make this happen. We have the 1 times d sub n x to the n, which eventually happens somewhere here. So we get a d sub n as one of the contributors. Then if we multiply this negative x by d sub n minus 1 x to the n minus 1, we'll get something that is an x to the n term, and the contribution will be negative d sub n minus 1. Similarly here, we'll get a minus dn minus 2, and then a plus dn minus 4, and then a plus dn minus 5, and then finally a minus dn minus 6. Now you notice here that we'll see this term whenever n is greater than or equal to 6, because when n is less than 6, we won't be able to write all these things down. Okay, but for n greater than or equal to 6, this coefficient of the series on the left-hand side is 0. So that means that this expression right over here has to be identically 0. Now if we look at this, we can rearrange this equation, set this to an equality here, and it would change all of these signs. And then as a consequence, we get a recurrence equation for the thing that we're counting. D sub n is this sum right over here with some differences in terms of the previous terms of the sequence. Okay, that's really cool. We can use this to compute explicit values for d sub n. And also, one of the things we have to be careful of is this only works when n is greater than or equal to 6. So we need to know what's happening when n is small. So how do we manage that? Well, let's look at, for example, the x to the 1 term or x to the 0 term of this expansion. Here we get 1 times d0, and on the left-hand side, our x to the 0 coefficient is 1, so that means d0 is 1. Okay, what about d sub 1? Well, if we look at the x term, we get d sub 1 minus d sub 0 as the contributors to the x term. So d sub 1 minus d sub 0 is whatever the coefficient on this side is, which is 0. So this is 0, and so we get d sub 1 is 1. And then d sub 2, by a similar argument, multiplying these, we have d sub 2 minus d sub 1 minus d sub 0 is the x squared term here, which is 0, so it's the sum of these two, we get 2. Right, and so we can keep doing this to figure out the first few coefficients, and then the rest we can use this recursion. Okay, so a cool way of going about this, if we don't want to find an explicit formula because the calculations might get messy, as we'll see. But let's go ahead and actually dive in and try to find an explicit formula for this thing that we can just plug in to a calculator or use our hands to plug into and take a look at what that looks like. So the method for doing this is going to look like the following. First, I'm going to factor each of these denominators. So here, I have a factor of 1 minus x and a 1 plus x squared as another factor. Here, I'll have a 1 minus x and a 1 plus x. And here we just have the 1 over 1 minus x. So let's collect like terms. All right, I want to write this slightly differently. So if we think about this, this came as one of the factors of 1 minus x cubed. So this is 1 minus x times 1 plus x squared. And we actually can calculate what the roots of this particular polynomial are. 1 is one root, that's why we got this term. And the other two roots look like omega and omega squared, where omega is e to the 2 pi I over 3. So this is a complex number fact, and if you want to know a little bit more about roots of complex numbers, I suggest like a video like this one. Even though it's titled GRE Math Subject Test, it still talks about complex numbers and powers, so you get an idea of what's going on here. So if omega and omega squared are roots of this thing, if we think about x cubed minus 1, it'll factor into x minus 1 times x minus omega times x minus omega squared. And so this thing here will factor into omega minus x times omega squared minus x. Okay, it'll be advantageous for us to actually write this a little bit differently. It'll be advantageous to write this as products with 1 minus things in them. And we'll see why in a little while. So it'd be nice if we could transfer to that. And we can actually do that by doing a slightly slick maneuver where we multiply this entire expression by omega cubed. Now omega was a third root of unity. It was e to the 2 pi I over 3. So this quantity actually is 1. Another way to think about this is omega was a root of this polynomial, so omega cubed is 1. So if you multiply by omega cubed, it doesn't change anything. However, we can distribute this so that we multiply by omega squared in this factor here, and omega in this factor here. Right? That will make this expression omega cubed minus omega squared x. Omega cubed is 1, so that would be omega squared x. And similarly here, we'd have omega cubed minus omega x. Omega cubed is 1, so we get omega x. And so here's a different way to factor the 1 minus x cubed piece. And since we've already extracted the 1 minus x part and put it over here, this is a factorization of this particular rational expression here, or the denominator of this rational expression. So let's go ahead and actually write that in the expression that we have here. So collecting the linear factors of the denominator, we get that f of x is 1 over 1 minus x cubed times these 3 linear factors. What we're going to do now is something that happens when you take a calculus course and you're integrating, which is to represent this as a sum of series using partial fractions. So how this works is we can write this as a sum of different rational functions that will be easier to deal with. So this denominator has a third power of 1 minus x, so we'll get something like a over 1 minus x cubed for some constant a, and then a b over 1 minus x squared, and a c over 1 minus x. And then each of these terms will get their own fraction with a constant in the numerator. Okay, so this series actually is the sum of all of these series right over here. So how do we determine what a, b, c, d, e, f are? This is something that you learn when you're doing partial fractions decompositions in integration in calculus. The way to go about this is you find a common denominator to re-express this in terms of this, and you'll get a really large set of polynomials in the numerator with these 6 unknown coefficients beside them. You expand all of those out, you'll get some polynomial, and then coefficients in terms of these unknown variables for each exponent. And you compare to the fact that when you place these with a common denominator, it has to be identically the polynomial 1. And so you get a system of equations in a, b, c, d, e, and f that you can solve to figure out what these coefficients a, b, c, d, e, and f are explicitly. So you can imagine this would take a lot of work. So what I'm going to do is erase the board and actually show you the final result when you do that computation. So here's the result of doing that entire laborious process of finding the coefficients. They're all right over here. And so now we're going to use this to find an explicit expression for the x to the nth coefficient of f of x, which is exactly the thing we wanted to extract, which gives us an explicit formula for the number of solutions of this thing. All right, so for some of these, we kind of already know what the answer is. So I'm going to highlight these in a different color. So some of these, we can get the answer quite quickly using power series expansions. So for example, here, we'll get that this expands to the sum of 1 plus x squared plus x cubed, etc. So the contribution here is going to be a 17 over 72. because that's the coefficient of x to the n regardless of what n is. We can do a similar thing for each of these three series right here. Here, the x to the nth coefficient is going to be a negative 1 to the n. Thinking about this as 1 minus negative 1x. We have to multiply by this 1/8 constant, so we'll get 1/8 times negative 1 to the n. Here, similarly, we'll get 1/9 times omega squared raised to the n, and here we'll get 1/9 times omega to the n. Okay, so that takes care of all of those coefficients. And so now the question is, what about these other two? So what we'll do is think about these pieces right over here and how to find their coefficients, and we'll use calculus to do this. So if you start with 1 over 1 minus x, its Taylor series expansion is 1 plus x squared plus x cubed, etc. All right, so to get an expression for 1 over 1 minus x squared, we can actually differentiate this. The derivative of this is 1 over 1 minus x all squared, and then the chain rule will have the negative cancel with the negative 1 that we get from the differentiation process. So this is the derivative of this, which means we can differentiate this to figure out what this series looks like. So differentiating, we get 1 plus 2x plus 3x squared plus 4x cubed, etc. Now let's do that differentiation one more time. I'm going to write this out over here because we won't need the series 1 over 1 minus x. We know that one. So if we differentiate this, we're going to get 2 over 1 minus x all cubed. Now differentiating this, we get 2 plus 3 times 2x plus 4 times 3x squared plus etc. So we can kind of see what's happening with these coefficients. Here we have to divide by 2 to get the coefficients of 1 over 1 minus x cubed. If we divide by 2, we get something like this. All right, so we can read that the coefficient for this part of the series here is going to look like whatever we see in these coefficients. Here, for example, we see that this quantity is n plus 2, like here we have a 1, times m plus 1 over 2. So here we'll get m plus 2 times m plus 1 over 2. And similarly here, we'll get the coefficient of x to the n as m plus 1. And so we end up with the final answer that looks something like this. D sub n is this fraction right over here, plus this fraction right over here, plus this entire expression right over here. So this is great, but it's also really kind of crappy. So the reason is, if you look at the answer, you're still left with something that looks like it involves complex numbers. That's kind of unfortunate. So that's a little bit of a problem. And it's not even clear why this number is an integer. The answer should be an integer at the end of the day. So we'll make one observation that would help us get to an understanding of why this thing works out the way it does. So this number here is actually an 1/8 plus a 1/9. And you notice there's an 1/8 coefficient here and a 1/9 coefficient here. So I'm going to rewrite this by adding the 1/9 to this piece and adding the 1/8 to this piece. So the reason I mention this is because these values over here actually end up being integers themselves, regardless of what n is. So for instance, here, what happens is we're taking 1 plus a power of omega squared plus a power of omega. So you can think of this thing as taking omega to the n and plugging it into the polynomial 1 plus x squared. Now this quantity here is either going to be omega, omega squared, or 1, because omega cubed is 1 itself. So as a consequence, because we knew and used previously that omega and omega squared are roots of this polynomial, this thing is either going to be 0 or 3. So at least we can resolve that this part is going to be always an integer. And here, this thing will always be an integer. If n is even, this quantity is 2, and if n is odd, this quantity is 0. So that gets us part of the way, but I'll leave it to you to think about why it's the case that this expression would have to be an integer regardless of what n is. All right, so a really cool way to actually explicitly find formulas for counting that started with expressing our counting problem in terms of generating series and then using power series expansions to actually get an explicit formula for the thing we're trying to count. So I hope you liked today's video. If you did, definitely click the like button. And if you want to see more videos like this, subscribe to the channel.